Question 2. A uniform T-section beam is 100 millimeters wide and 150 millimeters deep, with a flange thickness of 25 millimeters and a web thickness of 12 millimeters. If the limiting bending stress for the material for the beam are 80 megapascals in compression and 160 megapascals in tension, find the maximum UDL that the beam can carry over a simply supported span of 5 meters. Question 2. Okay, so the only slight complication with this question is that we are not told where the neutral axis is. So the first thing we're going to have to do is take moments of area around our shape to calculate where the neutral axis is. So let's consider my shape, and that's made up of, that's equivalent to this section here, top section, plus bottom section. So this is 100 millimeters wide. This is 12 millimeters thick. Top is 25 millimeters. And the overall height is equal to 150 millimeters. Okay, so we're going to take moments around this bottom axis here. Moments of area. Okay, so if we take this area and multiply it by the distance to its neutral axis, that distance y, that's going to be equivalent to this shape taking moments around this same neutral axis at the bottom, the same axis at the bottom. So that distance there is my neutral axis for that shape. That distance there, which is going to be 150 minus 12.5. So what's that? 137.5. 137.5 millimeters. And then let's consider the bottom now. The distance to the neutral axis of that part, this bottom section, is 150 minus 25, so that's 125. So the distance to the neutral axis is going to be 62.5 millimeters. So this section here is going to be 100 times by 25, so that's 100 times by 25, so that's the area of the top section, plus 125 times by 12, so this is 125, so it's well, that's 150 minus 25, so 125 times by 12, so that's the area of the bottom section. This is millimeters times 10 to the minus 3 times 10 to the minus 3 times 10 to the minus 3 times 10 to the minus 3. So we're going to have to multiply that by times 10 to the minus 12 to get that into meters. And so that's my area. And then we can multiply that by y. So it's going to give me my moment of area. My area times by this distance to the neutral axis. And we're going to say that's equivalent to, what have we got here? We've got this area times by this distance, and this area times by this distance. So this area is going to be 100 times by 25 times by 137.5 minus 10 to the minus 9 this time to get that into meters. So that's my area. That's my distance to the neutral axis. So therefore I've got some moments of area plus 125. That's this distance. 125 times by 12. This distance. So that's my area. Times by 62.5. 62.5. And again, I'm going to multiply that minus 10 to the minus 9 to get that into meters. So I'm saying my area minus by my distances from my neutral axis for the overall T shape is equal to my area times by the distance to the neutral axis for the top section plus my area times by the distance to the neutral axis for the bottom section. And if I do all of that, I'm going to end up with 4,000 10 minus 9. Y is equal to the top section, which is 3, 4, 3, 7, 5, 0 minus 10 minus 9 plus the bottom section, which is 9, 3, 7, 5, 0 minus 10 minus 9. If I will therefore look at what y is, therefore y is equal to 109.4 millimeters. So I've taken moments of area for my overall shape. I've said that's equal to moments of area for my two components, and therefore I can work out what y is. What is the distance to my neutral axis? Okay, now that we've got the distance to the neutral axis, we can work out what I is for the overall shape. So I, for our overall shape, I is for my T section. So let's draw my T section. We're going to say that's made up of two components. That's equal to, we consider the top section first of all. Let's calculate the second moment of area of that rectangle and then subtract that rectangle and that rectangle. So my overall shape minus this shaded region minus this shaded region. And then I'm going to add on to that same axis, a bit on the bottom this time. And add on this part here. Okay, we know this distance now is 109.4 millimeters, which we've just calculated. If we calculate this here, so that is 100 wide, so B times by D, so that is going to be 150 minus 109.4, so 150 minus 109.4, that's B cubed over 3 minus, so that's going to calculate the second moment of area of this outside shape, minus 2 lots of the second moment of area of the inside shape. So the inside shape these shaded regions. If this is 100 wide overall, half of that is going to be 50, so that's where that 50 comes from, minus half of the center web. And so that is 12 millimeters wide, so half of that is going to be 6, so minus 6. So that is B, that's how wide these are. And D is going to be 150 minus 109.4 minus this top section here, which is 25 millimeters. So minus 25. So that is B cubed over 3 plus this bit on the bottom here. So that is 12 millimeters wide, 12 times by this distance here to the neutral axis, which we've just calculated, 109.4 cubed, so BD cubed over 3. And then everything, we've got meters to the 4. This is millimeters cubed. So we need to convert that to meters to the 4. So times 10 to minus 12, which gives me a value for I of 7.36 times 10 to the minus 6 meters to the 4. Will be my second moment of area for my T section. Okay, so let's consider what we've calculated so far. We've got our T section beam. We've calculated where the neutral axis is. So let me draw my neutral axis. We've said that is equal to 109.4 millimeters. And we have now calculated the second moment of area of that shape, I, which was 7.36 times 10 to the minus 6 meters to the 4. So let's now try and answer this question. So what does the question actually ask us? The limiting bending stress of the material for the beam are 80 megapascals in compression. Okay, so stress max equals 80 megapascals in compression. And sigma max equals 160 megapascals in tension. Find the maximum UDL. So in order to find the maximum UDL, that's obviously going to be related to the moment. So we need to work out what is the maximum moment that is available, that we can carry in these two limiting cases. So we know from the simple theory of elastic bending, M equals sigma I over Y. So in this first case, my stress is 80 megapascals. So that's 80 times 10 to the 6. And I, which is calculated as 7.36 times 10 to the minus 6. Now, if this is in tension, in compression, the compressive stress is going to be on the top surface. Now, this thing is 150 mil, so overall height. So the distance from the neutral axis to the top surface is going to be 150 minus 109.4. So that's going to give me 250 minus 109.4 times 10 to the minus 3, which is 14.5 kilonewton meters. So that's the maximum compressive stress. The maximum for the max, so to get the maximum compressive stress, that's the moment that we need to carry. Now, for the maximum tensile stress, what moment must we carry? Now, so my moment equals sigma I over y equals 160 megapascals this time, so 160 times 10 to the 6 times by 7.36 times 10 to the minus 6 over maximum tensile stress is going to be on the bottom surface, so that's 109.4 millimeters away from the neutral axis, so that's going to be 109.4 times 10 to the minus 3, which is going to be 10.76 kilonewton meters. So if we carry that moment, we will see 80 megapascals on the top surface. And if we carry that moment, we will see 160 megapascals on the bottom surface. So therefore, my limiting case is that we go above that moment, we'll exceed that lower stress, or that tensile stress on that lower surface. So the next part of the question, we then need to calculate, okay, well, if that is the moment, the maximum moment that we can carry, what UDL must we, what is the limiting UDL that we're allowed to carry to get that moment? Okay, so let's now consider our situation. Okay, so we've got our beam. It's simply supported. So we've got some reaction load, different colour. Some reaction load, RA, another reaction load, RB. We've got my UDL on top of my beam, which is some load. Let's call that X newtons per meter. We want to calculate the limiting case, so we're going to need to consider the moment in the center of the beam, XX, and we now know that moment needs to be limited to, so MXX equals 10.76 kilonewtons per meter. So let's work out one moment. We know this is set in equilibrium, so we know our sum of our vertical forces equals 0. So the sum of my upwards forces equals the sum of my downwards forces. So the sum of my upwards forces are RA plus RB equal to sum of my downwards forces. Sum of my downwards forces are X newtons per meter times by the length of this thing, and this thing is, how long is this beam? This beam is 5 meters long, times by 5. So 5x equals RA plus RB. If they're uniform and equal, they're going to be half of that. So RA plus RB both can be the same. So therefore, RA equals 2.5x. So let's now consider my beam. I'll go halfway along my beam. We've got RE here. We've got X newtons per meter on top of the beam. X newtons per meter. We're in the center of the beam. This position here, XX. Looking left, what do we see? My moment is equal to my clockwise moments minus my anti-clockwise moments. My clockwise moments are equal to 2.5x, so that's RE. And how far away is that? That is 2.5 meters away. So that's my moment, my force, and my distance, minus X newtons per meter on top of the beam, times by 2.5, half of the beam. It's the magnitude of the UDL to the left of the middle, times by 2.5 over 2. We're going to assume that that is acting in the center. Okay, so the distance from here to here is 2.5. So therefore the distance from here to here is going to be 2.5 minus half of that. So 2.5 divided by 2. Now we know the maximum moment that we want is 10.76. So 10.76 equals that lot. It's equal to 3.125x. So therefore, x equals 10.76 divided by 2.125, which is 3.44 kilonewtons per meter. So that's the maximum UDL that this beam can carry, 3.44 kilonewtons per meter. Question 3. A T-section bar has dimensions as shown below. If the bar is used as a simply supported beam of span 1.5 meters, calculate the uniformly distributed load that can be applied if the maximum tensile stress is not to exceed 100 megapascals. Question 4. A column section is built up by connecting two 305 millimeters by 102 millimeter channels using battens. If the column is to have equal second moments of area about the two axes of symmetry, calculate the spacing, 2p, required between the two channels. Note that the battens do not contribute to the second moments of area of the section. Okay, so questions 3 and 4. Now, I want you to have a go at trying those questions on your own. Okay. Now, question 3 is very similar to question 2, actually. We've got a T section. We have to calculate the uniformly distributed load, which can be applied if the maximum tensile stress is not to exceed a certain value. So you need to approach that in the same way that we did in question 2. So the first thing you're going to have to do is to calculate where the neutral axis is by taking first moments of area around the bottom of the T section. Once you've done that, you can calculate the I value for the T section. You can calculate the second moment of area of the T section. Then you can calculate what the limiting moment is to give you the stress, which is not to be exceeded. And then once you've got that limiting moment, you can then work out what the UDL is to give you that limiting moment. For question 4, we've got a compound section this time made up of these 2 C channels. So we've got one C channel which looks something like this. We've got another C channel sat next to it, and we're told the properties of those C sections, C channels. Those are then connected with 2 plates. So we've got one plate on the top, and we've got another plate set on the bottom. So we're asked to calculate how far apart those plates need to be. So if we consider this to be the center of my section. So what is this distance here? Let's call that P, pitch of the plates. So what does P need to be in order to get the same second moment of area around the global x-axis? So let's call this XX. And YY run down the center there. So we need to calculate IXX for the entire shape. So the 2 channels and the 2 plates, add all those together. We then need to calculate what IYY is for the 2 plates, and then we're going to have to use the parallel access theorem. We know III one channel, and we need to offset that to the global vertical y-axis. So what is IYY for the entire shape? That clearly is a function of P. And then we need to equate IXX and IYY to work out what P needs to be to give us the same second moment of area. Okay, so have a go at those questions. Have a go at question 3 and 4 on your own. Any questions, let me know, and we can have a look at those questions in class. Okay, cheers, thank you, bye-bye.